Welcome back, everyone, to the eCoreAcademy e-learning platform today. My name is AJay Raj, back with yet another geometry video for you all. And of course, our lesson topic of focus for today is on tangent, secant, and inscribed angle theorems. So we're going to be taking what we've known as our precursing and previous knowledge throughout this course, and of course throughout geometry. We're going to be applying them to more complex circle function and circle circumstances. So we're going to take these lines and these products and parts of lines. We're going to develop these separate theorems that correlate these specific circumstances in circles together under these three given criteria. But before we jump into today's lesson, please make sure to smash that subscribe button down below, hit that like button on this video, as well as turning on post notifications by clicking that little bell icon right next to that subscribe button. All three of those things are very greatly appreciated, and feel free to comment down below. We really do appreciate all of your feedback, and we will try and implement them in all of our videos to come. As I was saying, today's main topic is to focus on the advanced theorems that correlate with tangents, secants, and inscribed angles in circles under specified circumstances. So as you know, the more specific that we get, we start to venture off from the general. So we start with our general topics with, circles or circle unit. Then we start to narrow into tangents, secants, arcs, chords, all of these properties of circles. And then we're going to try and correlate them together, which is even more specific under specified circumstances. So, of course, we're going to increase in difficulty. So I strongly recommend that you watch the predecessing videos to this topic on tangents and secants, arcs, and chords as well. I also refer to some basic theorems there, so that'll be a great opener and great opening to this video, as well as a great refreshing review before jumping to this so that you don't get confused. But without further ado, let's jump right into it. So let's take a look at what these advanced theorems are and what they actually represent amongst each other and amongst the different properties of circles and circles alike. So these are the special circumstances. So when looking at unique intersections and placements of lines and segments belonging to circles, relationships are developed. So that does not go without saying that it's not just your lines and your segments that are being identified. So after your lines and your segments are developed, such as your tangents, your chords, or your secants, once they're developed, certain intersections can occur and some might not. These placements in these specific circumstances, not only do they develop relationships among lines, but they also develop relationships to the actual circle itself, as we know, between sectors, also arcs, which are measured in degrees, central angles, inscribed angles, so on and so forth. So these relationships can be characterized by the following theorems, and I have included a series of theorems. It's not too long. There are multiple more, but I will be relating them and correlating them with later topics to come in the future, also in this circle and conic sections unit. But for now, we're going to be focusing on those that specifically entitle to tangent, secants, and inscribed angles. So if we take a look here, we have this special intersection of two radii and two chords. So as you can see, we have those two radii, AC and AD. They're both intersecting at the center, of course, because they're radii. They're going to have the same originating point. And then if you have chords that intersect both sides. And these are some specific circumstances in which you're creating inscribed angles. These angles within are called your inscribed angles. So arcs equal inscribed angle. And then you have your chords here, which I'll mark off with a little Z here, your break. These are your chords, so Z or break is known as your chords. And then finally, you have your generic radii, which is always going to be consistent with a circle. And of course, that's just a common part of a circle that we've already gone through before. So nothing really new here, just trying to elevate them with specified circumstances and correlate them with each other. So let's jump into our first theorem. Circle theorems part 1. Let's look at the tangent perpendicularity theorem. So when a tangent intersects a circle, it will only intersect the circle at one point called the point of tangency. Now we know this from our previous videos that a tangent is tangent to a given circle at the point of tangency. And at this point of tangency, that given tangent will be perpendicular to the given circle. And how is that true? It's going to be perpendicular to the given radii. Now we know that radii are infinite. Radii are infinite, not finite. So if they're infinite, that means we have a numerous amount of radii, but we have a general idea of where they consist of. But there will always be one radii of focus that will automatically be perpendicular to a tangent at any intersection of your given circle. Now you can utilize the Pythagorean theorem when given this situation. So if we look here, we have tangent AB. So AB is this line down here, and then we have circle O, indicated by its center. So when AB intersects or makes contact with circle O, it'll have one radii, circle O will have one radii that'll be perpendicular to this given tangent, and that's always the case. So this right angle will form 90-degree angle, perpendicular, intersects at a 90-degree angle. And when it intersects at a 90-degree angle, what we can do is we can develop an equation in such that O can meet on any other part of AB, line AB. So originating from the center, we have this line called S, and it's going to intersect. It's going to be a line segment that stops at a point on AB. And once that's actually developed, we can see here that 90 degrees has been developed here, and we can utilize Pythagorean theorems. For given the length of AB and OT, we can develop our hypotenuse of MO, so that you can utilize the Pythagorean theorem, a squared plus b squared equals c squared. And also, if we have special types of right triangles, which I will get into later in our later lessons, but like 45, 45, 90, and 30, 60, 90 triangles, you can also develop theses on your angle measures as well, utilizing this theorem. Circle theorems part 2. Let's look at the secant-tangent theorem. So I've already referred to this as I have the previous one. I've just gotten you guys to open your eyes up to them and get familiar with these terms, but today I'll be going under further analyzation with you. So when two tangents, two secants, or a tangent and a secant intersect, so this is basically correlating all possible relationships between intersections of tangents and secants, or both of each. So when two tangents, two secants, or a tangent and a secant intersects, the angle that they create exterior to the circle is the average of the intercepted arcs. So utilization of the Pythagorean theorem is also available here, but I will explain that later on in later lessons. It gets a bit more complicated when you have arcs, but I just want to put out there that when you have arcs are actually just pixelages. So that means they're straight lines formed. One pixel is a straight line. Technically, it's a dot, but that is identified more as a straight than a curve. And a curve is developed by multiple pixels being connected together. In turn, it's being basically a straight line is being bent, but it's a multitude of straight lines creating your given arc. So if we're going to look at our tangent secant pattern here, we're going to look at a MO and MQ, which is two secants. If we know how this works with two secants, we can automatically apply it to two tangents, and likewise with a secant and a tangent, which I will also get into in our last slide. I'll go under another specific circumstance of that. So that's why I wanted to choose the secant and secant intersections on the outside. So they intersect at M here, and what we're looking for is the degree measure of angle M. So we're looking for the degree measure of angle M here. So how are we going to discover that? Well, if we look at this intersection here, both lines will connect and intersect at arcs NP, that arcs NP, and arcs OQ. Now, if we're given the degree measures of these given arcs, we know that NP is going to be less than OQ, but in this case, I'll give you an example. So if we have 32 and 64, all you're going to do, it's going to be in degrees. Arcs are also measured in degrees, just as an FYI. So all we're going to do is we're going to average out both of these angle measures in order to get the measure of angle M. So if we add those together, 32 plus 64, we get 96. 96 over 2 equals 48. So now that we know that the average of the both is 48, we know that our angle measure here is going to be 48 degrees. On to the next theorem. So circle theorems part 3. Let's look at the intersecting chords theorem. This is a very interesting one that I kind of found confusing a bit more, but it's a very simple concept. A lot of times geometry tries to trick you and correlate this with another type of theorem that has to do with secants. Make sure that it's either identifying it as chords or that you're being given line segments. Because remember, chords are line segments, secants are lines. That means they're not always on the interior of a circle, just a small part of them are. Or an unidentified part of them are not. That's how we should explain that. So when two chords intersect in a circle, the product of the segments on the same chords will be equivalent to each other. So this is basically how cross multiplication, such as in Japan, they don't actually do formal multiplication in order to show you. They don't do elongated form where they stretch everything out, and they only show you the simplified form. But in Japan, they use lines just as such to explain how cross multiplication works, and that's kind of where this chords theorem really started to set foot. So you can substitute in values for x in these scenarios, so that's more of the problem solving part of it. So if we're given these two chords in this circle, let's name this circle A. They're both intersecting on the interior, of course. They're going to be all located on the interior. And at this intersection here, it's going to split each given chord into two different parts. One part is going to be much smaller than the other part. So if we're given that this part of this chord here, x and 15, those are the two different parts of our given chord here. We have 9 and 5. So what we do know is this side here, 9 and 5, this line segment, the two parts of this given chord multiplied together is going to be equivalent to 15 times x. So 9 times 5 must be equivalent to 15 times x. That's all it is. When you're multiplying these together, they should equal each other. So let's do that here. So since we have a variable, obviously we're going to be solving for x. So we have 9 times 5, which equals 45. And then we have 15x. So those are the two multiplication sequences here. So now that we have that equation there, we know that 45 equals 15x. We're going to divide both sides by 15. And we get that x equals 3. So that's the answer, x equals 3. If we check that, 9 times 5 is 45, and 15 times 3 is 45. So right here. Multiply segments. And then over here, I'm going to say show as equals. All right, let's move on to our next theorem. Circle theorems part 4. Let's look at equal products of secants. So this is going to be very similar as well. So when two secants have a common point of intersection on the exterior of a circle, the segments formed will have equal products. So this is going to be the same scenario in which you have two secants intersecting on the exterior, just like our arcs formed. But now in this case, we're going to be looking at the length of the line segments instead of angle measures. So you will multiply the segments of each secant similar to just as you did with the intersection of the chords. So if we look here, same exact example, MO is our one secant here, and then MQ is our other secant, and they both intersect at point M on the exterior of the circle. Now what we're going to be comparing is, if we're given a length of, say for example, MN is 4, and NO is 6. We know that MP is 4, and we're given that PQ is X. Now, what they're basically saying is once this line MO, the secant MO, intersects the circle, that's one segment formed. And then the rest of it on the interior of a circle, the chord in the interior is a second part, likewise with MQ. Now, we know that the product of these two must be equivalent to the product of these two. So since we're solving for x, let's multiply these out. So 4 times 6 equals 24. And then we have 4x. Secant 1 and secant 2. So we'll solve for x, set them as equals. 4x equals 24. Divide each side by 4. We get that x equals 6. Moving on to the next theorem. Circle theorem is part 5. Equal ratios of secants and tangents. So this is going to be looking at ratios of secants and tangents. So when a secant and a tangent both intersect on the exterior of a circle, then the interior part of the secant multiplied by the exterior part is equivalent to the square of the tangent. I know that's a mouthful, but it's more of just numeric values and plugging these values into this formula. So I personally have memorized them after constant utilization through practice. Remember, for math, it's not helpful to just memorize formulas if you don't actually practice them. So memorize them through practice. Memorize your practice. If we're given this example here, likewise. So you're going to have a tangent instead. So a tangent and a secant intersecting instead of a secant and two secants intersecting. So you're going to have a tangent UV. and your secant uy. So when these two intersect on the exterior at a common point, such as u, all it's saying is we know that this exterior part of the circle, this part of the secant is ux. Given that ux is 8, and also that xy here is given as another 8. Let's assume that's 8, although this is not drawn to scale, but this exterior part is not given its own part here. So let's assume that these are both 8 and 8, and we're given that uv is worth x. Now we know that the multiplication, so once we multiply 8 by 8, we get 64. So you're going to multiply the exterior part by the interior part. And we know that the tangent is equivalent to, we know that this secant, this 64, the product of these two values, is equivalent to the square of your tangent. So that means 64 equals x squared. So we square root both sides. We get that x, sorry about that, x equals 8. Alright everyone, so that'll be it for today's video. I hope you all enjoyed. This has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe down below and turn on post notifications, and feel free to leave a comment down below. Check out our website at www.ecoreacademy.org. There we have full unlocked access to what we as an e-learning platform actually offer for you. Full unlocked quizzes, integrated quizzes, note sheets, and worksheets that go along with each and every one of our videos, specialized just for you. All you have to do is make an account for free. Feel free to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out. And finally, visit all of our socials in the description box below at Facebook, Twitter, and Instagram. Use our mediums to share all of our videos and see what kind of interesting content and unique content we have out there. Once again, everyone, that'll be it for today's video. I hope you guys enjoyed. This has been AJ, and I will see you guys in the next one. Peace.